chapter of dynamic programming, and we derived the linear quadratic regulator. We stated the Bellman equation. But now I want to come back to dynamic programming, not the stationary solution, but just dynamic programming as an operation from one time step to the previous one, and extend it to robust and stochastic systems. And from my personal point of view, the fact that we can do dynamic programming for robust and stochastic systems justifies the existence of dynamic programming, because for most other problems it's really it can be outperformed by online optimization, but for robust and stochastic systems there is some case for it, and the reason is that the complexity of the algorithm does not increase with robustness or stochastic. So when you don't include, when you include these uncertainties into your system, dynamic programming will still be as expensive as it was before. I have a question about the sound. It's again disturbing me a bit. Okay, for you it's okay, or is it not loud enough?
When you come close,
Sorry?
when you come close, it makes some echo.
Yeah, exactly. It makes some echo at some point. It feels always as if I had something in my ear or something. I don't know. Good. So let's start with robust dynamic programming. Robust system or robust design is actually concerned with assuming that we have an adverse player, someone who is against us. And the control of this adverse player we call WK. And every time step this adverse player can choose a W against us. And this choice might influence the stage cost for the next stage, but also, and this is most important, the system dynamics. I put index I at everything here in order to express that this isn't restricted to autonomous systems. So we could have time-varying systems here. So, but what you have to do in dynamic programming is quite simple to derive. What you want to choose the control that you can choose, so that whatever the other guy does, so the adverse player, which could be nature playing against you actually, but it could also be in chess, the other player, has no possibility, so to say, to make, you minimize the worst case. Yeah? So you look what are the possibilities that the other guy has, and you choose the one where the other guy has the least chance to beat you, so to say. So nature wants to, or the adverse player wants to maximize. I think I will just remove myself from this screen and remote control it from the back to avoid the echo. So you choose the max, the min of the max. And this function that we minimize, I always call J tilde, just for you to know. And J tilde is, of course, a function of x and u. It's already the maximum of all the adverse player's choices. And of course, I start again with my end cost. So for chess, you could imagine that something like I win is 0, and the other guy wins is 1, yeah, as a terminal cost. And you could look at all terminating states and give them a cost, and then try to go backwards until you find the state in which you are now. I mean, this is the state space in chess is so incredibly large that people don't do it this way, but approximately you can try to do it also for chess. The other case that we want to look at is where the system is stochastic. So here we assume there is really a bad adverse player who is always playing against us, doing something as nasty as possible. But in stochastic systems, we would just assume there is some probability distribution of these W's. So there are some other actions we cannot influence, but there is just randomness influencing them. And then we arrive at stochastic dynamic programming. So we still have this W, but W is now, we call it a disturbance, and we don't assume that someone is actually playing against us. It's just random. And then we have a similar setup. We would just minimize the expected value of the next stage cost plus the expected value of the expected cost to go after one time step. And here we need to take the expectation over all realizations of W, and W is now a random variable that might depend on X and U. So it might be that the probability distribution of W depends on X and U. That's why I introduced this P of W given X and U. And at the bottom here you see how we define the expectation of some function. If you have finitely many realizations, so if you have 3, 4 realizations, you could just weight them with the probability that each of these scenarios takes place. So what is interesting here is that, again, after you take this expectation, you have a function of X and U, nothing more. I call it J tilde again. And the complexity is still, the main complexity of dynamic programming is that you have to store in state space your value function. That's the real problem, right? Of course, here you also have to evaluate this expectation operator, but you have to evaluate it once in this iteration and once in the next one. While if you would do this with some other methods, which also exist, if you have finite horizons and you have finitely many scenarios, you could end up with what we call scenario trees. But a scenario tree will actually in every time step branch. So you have 3 possibilities now. You will have, for each of these 3 possibilities, you will have 3 possibilities in the next step. So that's already 9, and then 27, and it very quickly grows exponentially. What you would have to do with scenario trees. While in dynamic programming, you still have the same complexity that you would have without this stochastic perturbation. Of course, you suffer from the beginning from the curse of dimensionality, so you cannot really, I mean, it's not for free, so to say, but the method is from the beginning already so expensive that it doesn't get more expensive by adding robustness. And that's something interesting. There's some 2 properties I want to share with you about the dynamic programming from a more theoretical point of view. What dynamic programming does, it's actually something that you could interpret as an operator acting on a function. So this operator, very often we call it T. I give it an index K to express that it depends on time steps, possibly. So the cost to go we might call a value function, and the operator that makes from the future cost to go the present cost to go, that is something we call T. And T acts on J, so it acts on a function which you could imagine as a big vector like what you did yesterday, well, a lot of values, but it's actually a function. And it acts on it by minimizing, by first adding to it, so to say, by doing the dynamic programming operation. That means you take this function, you plug into it the system dynamics f of k, k, and you add to it the stage cost Lk, and you minimize over u. And this whole set, what you do with one j, and which gives you another j, you call it t. Tk, because the functions might depend on time. And so this normal dynamic programming recursion, you could just write in this form now, here this simple equation, where you just take the future cost to go, you apply the dynamic programming operator, and you get the present cost to go. It's just a very compact way, and this is of course a nonlinear operator. I mean, it's not a simple operator, but it takes, if you think of it in finite state spaces, it just takes a vector of numbers, namely the cost to go or the value function, and it produces another set of values. And now you could ask about the properties of this operator acting in function space. And there is one interesting and easy to prove property which I want to share with you, which is called monotonicity of dynamic programming. And that's very clean and clear actually. If you have one function j which is bigger pointwise than another function j prime. That means at every single point in state space, this j is bigger than j prime. Then you could actually apply this operation. You have it at the top line here. And you see, because the j is everywhere bigger than the j prime, there is no chance by minimization to make anything smaller when you minimize over these j expressions. So you preserve this. So you have tk of j is also bigger than tk of j prime. And so that's a monotonicity property which is very useful. in particular when you want to prove that somehow your dynamic programming recursion converges to something. So imagine, for example, why this could be useful. You could have a positive stage cost. Very often we have that in MPC. You could start with 0 terminal cost, so you have nothing. After one time step, when you take 0 and you apply dynamic programming once to it, you get a function which is bigger or equal to that because your cost is positive, right? So that's what would happen. And then you have a j and a j prime, and then you can show if you apply it recursively, you can only increase your cost to go. And so then you know it will monotonically increase. You might then need to find an upper bound, and if you have an upper bound and a lower bound, you know, point-wise it will converge to some values, and then you can show that it will really converge. So that's more of a mathematical interest, but it's also an interesting concept to keep in mind. Yeah? I should also say to those that are experts in stability theory for MPC that a lot of stability theory in MPC gets much easier to formulate once you use this operator T. So for example, positive control. So if you want to have a control Lyapunov function, it can be expressed in using the operator T. It's actually a function so that when you apply dynamic programming to it, it is actually lower than itself. Okay, but now I want to specialize another thing, and this is convex dynamic programming. That's something that I did not really find well covered in the literature, even though there exists some. If you Google for convex dynamic programming, somewhere you find people that use that word at least, but I think it's slightly different. So this is not really well exploited, or I'm not aware of it, but I think it's interesting, so I wanted to share it with you. And the observation is that certain dynamic programming operators preserve convexity of the value function. So, and that's quite general actually. So the assumptions are very simple. I mean, you would assume a system which is linear, any linear system, and it can be uncertain in W in arbitrary ways. So W could be anything, right? So the matrix A depends on W, the matrix B depends on W, and an affine term depends on W. So all possible uncertainties are allowed, but it should be linear in X and U, or affine in X and U actually. And the stage cost should be convex in X and U together. For example, quadratic stage cost would have this property, and again it's independent of W. So the weights even for these quadratics could be depending on W. So everything is allowed here. And then dynamic programming, robust dynamic programming, and stochastic dynamic programming, which all lead to different operators T, but all these operators will preserve convexity. That means if you take a convex function, you plug it into this this dynamic programming operator, you do one time step backwards, so to say, you get again a convex function. And the proof is relatively simple, but let's just do it in this generality. So you regard first the function that you need to maximize or take the expectation about. That's this L plus J of f. I dropped the index, but it's just for convenience. So if you fix W by the assumptions, this is a convex function. Why? Because the L is convex and the J is convex by assumption, right? And f is affine. Then you can either take the maximum over W or the expectation. Maximum is over of a collection of convex functions, preserves convexity. And expectation is actually weighting with positive numbers, so that also preserves convexity. So in both cases, this function J tilde would be a convex function. Or in all three cases, if you don't have any randomness, no W, of course it's also convex. And then you have a convex function in X and U together, it's convex, and then you minimize over one of its arguments, namely over U, and you get another convex function. That's also one of these interesting things that we treat actually tomorrow morning in more detail, the operations that preserve convexity. And yeah, the resulting value function that is minimization of this J tilde over one of its arguments is again a convex function. So that's the simple proof. And why could that be interesting? I find it, I mean, it's just interesting to know about it, also because very often we deal with linear systems which might actually be affected by uncertainty. And what I find important here is, I go back once, that your system can really depend on the uncertainty in arbitrary ways. So it's including the case of matrix uncertainty. Yeah? So the hard case, I would say, of robust predictive control. So we have convexity, and why could it be important? There are, I would say, 3 reasons that I find interesting, but there might be others. That's why I wanted to present it to you. So first of all, if you would somehow have this J tilde and store it or somehow keep that online, then you could actually get the feedback by local optimization, because it's a convex optimization problem, right? So that would be useful if for some reason you want not to store the J but the J tilde. Another thing is that you can represent the value function if it's a convex function. A convex function is something that has, you can lower bound it by hyperplanes. So you can actually take linear functions which are below your convex function, and you could actually use these hyperplanes to represent your function, for example, as the max of a lot of these hyperplanes. So that's actually the picture behind it is that you have some convex function here that is the J, yeah, the J, and you represent it by, not by tabulating in state space, but by tabulating in something like a dual space, namely in pieces that support the epigraph of your function. So that might be useful to represent a value function in high dimensions. Because it's, if you would just have a few pieces, you could have some decent approximation of a value function, which is at least a lower bound of your value function. And then in robust dynamic programming, there's another advantage of having convexity of the value function, and that is that in robust DP, if you look back what we do in robust DP here, you have to have this maximization problem in W. And this one, if you would imagine, for example, that you maximize over a polytope or something like this, then the question is, where will this maximum be taken? And if you know that the thing that is here inside the max operator is a convex function, then over a polytope, for example, this is another assumption I didn't write down here, but if you make that assumption, then you know, for example, because it's a convex function and you maximize it over some set with corners, it will actually, with vertices, this maximum will be taken in the vertices. So then you have an easy way to, so to say, evaluate the max. And that would allow you to prove that it's enough to test only the vertices of a polytope. So there are just some observations, and you never know what they could be good for, but I wanted to share them with you. That's actually all I wanted to say about dynamic programming on the discrete time side. And if there are no questions now, I would go to the continuous time case, where we want to rigorously make the step from dynamic programming to the Hamilton-Jacobi-Bellman equation by using a simple limiting argument, so that you get the full picture. This is more for, it's not, let's say, as research connected as the previous 2 sections, but it's education-wise, I think it's useful. So let's now look at the continuous time system again. So we leave discrete time optimal control, we go to continuous time. We have again a Boltzmann objective, we have a fixed initial value and some ODE. And now we want to look how we could apply dynamic programming here. And in order to bring it, so to say, to discrete time, we do something which we never do in practice, but we can do for theoretical purposes here. And that is we introduce an Euler discretization. That is, so to say, the simplest integrator that you can imagine for an ODE, where you introduce a time step, you divide the time horizon by n. We call this time step h. H is the length of your time step, the interval length. And then your a cost function can be approximated by a sum. All these little integral pieces you approximate by h times L, evaluated at some node values. And Si and Qi are now the states on the grid points. And you replace the dynamic system by this simple expression here, where you have, that was where your discrete time system would be, and you replace Si plus Hf of Si. That's actually one time step ahead. Are you on board with this discretization? Okay. So we transformed it by a very crude method to discrete time. And now we can actually apply dynamic programming without anything, assuming that this would be a good representation of the continuous time system. And when we make h small enough, it will be a good representation, right? The sad truth is that in practice we would need to make h incredibly small in order to make this useful. So in practice we do other discretizations, but they are much more tedious to write down, and there is, for the value, for the limiting argument, there is no difference. So let's now do dynamic programming for this Euler scheme, as we could call it. So then what we have is dynamic programming. I just write it down exactly as we did it. So we have the stage cost, which is now h times L. So there's this little h, which will go to 0 later. And there is the j evaluated at x plus hf. Yeah? So one little time step into the future. You see the front line is just the application of dynamic programming to the system that we had before. And because I want to go to limits in time now, I want to replace the index that I have now, which is standing for the time points. I want to replace it by an argument tk. It's just a name, a different name at the moment. So I write down the same thing by just saying there is not an index k on my j, but there is an index t on my j. And I call it tk. Tk is actually just the time point k times h on my horizon. So the second line here is nothing else than the first line, just with a different notation, in order to already introduce the t as some argument that enters the function j. Yeah, so I hope you're on board. So you see the second argument here, that is just saying that I'm at one time step to the future. Okay. And now we assume differentiability. That's a strong assumption, I should say. Yeah? But we make this assumption. Assume that this j is differentiable. And then you can just do a Taylor expansion. And you can use the fact that this h is small. And you just write down the same equation. I drop the k index just because it's not necessary anymore. And the main point is the Taylor expansion of this term here, where I have two small things, this h and this h here. And so it has a constant contribution. It has a first expansion in the x direction. That's the gradient with respect to x, I should say. It's not explicitly mentioned here. And here's the derivative with respect to time, which is then multiplied with h, because h is a step in that direction. And then all remaining terms are of second order in h. So h square. So in the limit, we can hopefully neglect them. And now, what can we do? We can bring all the terms. Yeah, let's still look at this equation. So we bring everything that is depending on u, not depending on u, to the left side, because we don't need to minimize over it, right? So in particular, this thing here does not depend on u, so we can bring it to the left side. And also this thing does not depend on u, so we can bring it to the left side. So this and this will just cancel, and this one will move to the left side and become a minus sign. And then the beautiful thing is every term that remains is depending on h. Yeah, so h is the thing that we want to make small. So here's an h, and here's an h, And here is an h, but that's on the other side. We don't need to minimize over it because it doesn't depend on u. And so we can divide by h, and then we get the equation that we wanted to get, namely this one. So it's already there. That is the Hamilton-Jacobi-Bellman equation. So we just had to make this very strong assumption, which is technically not always true, that the value function is differentiable. Yeah, and by, as I said, mathematically a rigorous theory, you can, so to say, make assumptions that it is approximately smooth and then go to limits, and that's what basically these viscosity solutions do. But if you would assume differentiability, everything would be nice, and you can derive it this way. And as said before, we would then solve this equation backwards by fixing the terminal condition of this J and going backwards in time. So that's already the part that I wanted to do on the Hamilton-Jacobi-Bellman equation. So now I hope that you are more happy with the derivations that we did yesterday afternoon. And of course, please keep in mind the optimal feedback control at some state, at some time, it's a space-time domain, right, would be obtained again by this minimization problem, the same that we have here. So you need to know the gradient of your value function, and from this gradient you can get exactly your feedback control, if you would know the gradient. Yeah, I already mentioned before that very often people abbreviate by introducing the Hamiltonian function, so I wanted to make you aware of this function. It's actually taken, it's something from continuous time optimal control. You take the stage cost, the integral Lagrange term, plus a lambda transpose times f. It gives together a scalar function which depends on x, lambda, and u. And this function is actually depending, as I said, on 3 arguments. But when you minimize over u, which in many cases you can do explicitly, at least in toy examples or in mathematical toy examples, and you minimize over it, then very often in the literature this is called h star of x and lambda. So it doesn't depend on u anymore because you minimized already over it. And sometimes that's called the true Hamiltonian in some papers. It's just the Hamiltonian evaluated at the optimal value u. And if you use this true Hamiltonian, then you can write down the Hamilton-Jacobi-Bellman equation in a very compact form, where you just say it's a differential equation, which is, so to say, an evolution equation of this function j, backwards in time, which is depending on a function h star, which very often, as I said, you can write down analytically, which depends on the location x in space and on the gradient of the value function. So it's not a diffusion equation, but you see the similarity to it. It's actually, I think it's a hyperbolic partial differential equation with some nasty properties, but it is in principle something that you could try to discretize in space and then solve, for example, with the method of lines that we mentioned also yesterday, if you want. Okay, and of course this is like just an exercise to rehearse and to make sure that we are on board here. I wanted to make the same thing that we did for linear quadratic problems once for linear quadratic problems in continuous time. And I use the same notation. I use Q and R and S for the weighting matrices, but now they depend not on an index, because time is not discrete, but they depend on time. So they might be time varying. And also my system A and B can be time varying. So I have now time varying linear systems. And for them I could derive actually the Hamilton-Jacobi-Bellman equation. And I can plug in my data. And the beautiful thing is that also here the value function remains a quadratic function. And how do we do it? We just assume, that's the assumption that will be proven to be right, that the value function is a quadratic by making this ansatz, x transpose p of t times x, and p of t is a symmetric matrix that we want to derive by an evolution equation. Then we say this is actually the Hamilton-Jacobi-Bellman equation. It's taking the stage cost plus the predicted cost of our Why do I have that? I forgot this. No, it's clear. So what I have here is the Hamiltonian, right? The gradient of J, exactly. So I need to take the gradient of J, which is this expression here, 2 times x transpose times p. That's the transposed gradient of J. And I multiply it with the system dynamics, which is ax plus bu, right? So that's what we plug in. And now you observe that this term at the right, it doesn't look really symmetric, but actually if you, it appears twice. So I can actually symmetrize it by transposing it. I mean, it's just a number, so I can transpose it and have it once this form, once the other form. And then I can summarize all terms. And I take the matrix that appears from this. This is a function of x and u. So I can just add it to my matrix here, and then I get this expression. So you see there is no squared term in u, but all the other terms get modified due to this p times a and p times b. And then I have a symmetric right-hand side, to which I can apply the Schur complement lemma like yesterday. So it's exactly the same lemma, actually. I just need to invert this r, because I minimize over u. There's this r inverse here in the middle, and then the other two terms on the left and on the right. And the term here at the top is preserved. And I get the derivative of j. And the nice thing is that what this j derivative, as a j derived with t, is a quadratic function. So j itself is a quadratic function, and its rate of change is a quadratic function. That basically means that my coefficients, or this matrix coefficients that describe the j, they are just changing in time. And so because the dj by dt is actually, assuming this ansatz at the top, is actually just p dot times x from both sides. You actually take away the x on both sides, so the product of x, and then you get a matrix differential equation, which is the one here at the top. It's minus p dot equal to some expression, and that is the differential Riccati equation. And I dropped here, just for notation, all the index t, but I should say that it's possible to have this equation for time-varying systems, so everything can depend on t. And of course, the p definitely depends on t, even if the rest is autonomous. And then you can use also the feedback law. By the Schur complement lemma, you get this feedback law. Yeah, so everything is easy. And you could say, okay, it's nothing added actually in practice to what we did in discrete time. And in fact, it is very related. And I think it's a good exercise and good to keep in mind that the continuous time and the discrete time dynamic programming, or Hamilton-Jacobi-Bellman equation, they share a lot. And yeah, sorry, this is like 2 slides before. But let's go in order. So I first derive also the stationary solution. So you could say, when is it getting the solution of the infinite time horizon problem? So you would first make everything autonomous, so nothing is allowed to depend on time on your data anymore. Then you integrate this equation backwards in time infinitely long until it's going to a steady state, which you hopefully find, and that is then characterized by p dot equals 0. And so I just state this equation here. And this is now an equation which is called the algebraic Riccati equation in continuous time. It's slightly different than the Riccati equation that we had in discrete time. You recognize it directly because the p is multiplied only once with an a, while in the discrete time it was multiplied with an a transpose p a, so with 2 a's. And then the feedback law is a static gain, and you can compute this k matrix also after you have solved the Riccati equation. So it's exactly the same. And now you could ask yourself, what is the relation between discrete and continuous time? I mean, you see from this Euler discretization, we somehow just discretize it, but x would still have the same units. I mean, x would be maybe temperatures or velocities or whatever, and u would also still have the same units, right? So this feedback law would be strange if this feedback law would give a different matrix in discrete and in continuous time. And indeed, this is the thing I want to point out. If you regard this transition from continuous time to discrete time, so on the left is continuous time, on the right is discrete time that corresponds to it, just using this Euler discretization because it gives you the right orders of magnitude directly. Your continuous cost becomes a discrete cost depending on h. And if you do this transition, J and also U star will basically remain the same. So they will not be affected by this h. So it doesn't make it like infinitely smaller one or the other. So you basically get the same feedback law and the same value function, I mean up to some discretization errors, because one is maybe an approximation of the other. But that also means that in the limit you get the same matrices P and K. So if you make, for example, a discrete time recursion and you refine your time steps more and more, you don't expect that the P will somehow grow or shrink or something. If you do it correctly, it will just remain and converge to some specific continuous time value. And the same for the feedback law, K. So they are not so different. Okay, this is just also as an exercise. You could also make this infinite horizon setting for the nonlinear Hamilton-Jacobi-Bellman equation. So you assume stationary cost L. This one is an error. You don't need it if you have infinite cost. You assume an autonomous system, and then you can formulate the stationary Hamilton-Jacobi-Bellman equation. And this is an equation. If you have solved it, you have solved basically the nonlinear, continuous time, infinite horizon problem, which would be a wonderful thing to have, right? I omit one thing which is mathematically involved. If you want to include stochasticity into the Hamilton-Jacobi-Bellman equation, this is also possible, but then we are in a very mathematically difficult terrain, taking the expectations pointwise and still differentiating functions and so on. So I don't want to embark on it, and I'm not an expert on it either. So let's summarize. The two equations I think we should remember are the Hamilton-Jacobi-Bellman equation and the dynamic programming equation. This one is most important and I think easiest to remember. The Hamilton-Jacobi-Bellman equation. You can also remember maybe the word what is a Hamiltonian function, because it's sometimes used in the optimal control literature. And of course, keep in mind linear quadratic systems can be solved analytically. And in some sense, and this is maybe interesting here, it's the easiest example of the larger class of convex dynamic programming. Yeah? So if you want to generalize LQR, one way would be to say, oh, I just generalize it by doing convex dynamic programming. Maybe I should say a few things for those that do explicit MPC, and we do it on Monday and on Tuesday next week. If you look at the value function in explicit MPC, which people very often don't, but this value function is actually a convex function, so it's a really useful property. And dp generalizes very easily to anything that's robust or uncertain. So that's the reason why I think it can be really interesting in some applications. That's it. I want to point out there's this very nice book by Dimitri Bertzikas on dynamic programming, which I recommend for everyone who is interested in knowing all details on dynamic programming. And this point of view towards optimal control, which is a very different one than what we usually take in this course. But it's the dynamic programming point of view. Okay. I think we are exactly 10 minutes before we start the next lecture, so let's have a short break and relax. Thank you.